Hey folks, in this video we're going to be talking about the quantum atom model, maybe atomic, but whatever. It's about to get real up in here. So a few objectives for this video. I want you to be able to generally describe the differences between classical mechanics and quantum mechanics. And I would like you to be able to compare and contrast the Bohr model and the quantum mechanical model for the atom. And I'd like you, really importantly, to be able to explain the, not the difference, but to be able to explain can't say this, it's a tongue twister. Shells, subshells, and orbitals, and the relationship between those three different terms. And so some new vocab will be subshell and also orbital. We'll be talking a little bit about those. You may have guessed it that subshells are related to shells. Anyway, let's get going. So quantum mechanics versus classical mechanics. Well, in classical mechanics, we get very definite answers to problems. So like if we do a calculation for like throwing a ball straight up, we can determine that it's going to land at your feet. There's no wind resistance and you toss it perfectly straight up. Or like if you push a ball up a hill, it will definitely roll back down that hill. Or we could say that something is at a very fixed definite position, like the electron is at this position known, right? Right there. So it's useful for everyday world, down to even how molecules behave. It's very great for doing lots of calculations, but it's really not good for describing the behavior of atoms or even subatomic particles, more specifically very tiny subatomic particles like electrons, which are very little. The smaller things are, the more useful quantum mechanics is. In quantum mechanics, we don't get great answers for everyday life, but if we're studying tiny things, as I said, it's really great. We get these answers that are based on probability, not definite answers. So if you throw a ball up in quantum mechanics, you might get answers like, hey, there's an 80% chance it'll land at your feet, or there's a 15% chance it'll land behind you, and there's a 4% chance it'll land somewhere far away from you, and there's like a tiny 1% chance that it'll never land ever and it'll fly up into the cosmos. This is more of like a quantum mechanics answer, where we have something that's likely to happen, but then these other things that we can't rule out because they are somehow possible. And if we're describing the electron, instead of saying that that electron lives right there, we would say, hey, there's a 70% the electron is right there, but there's also a 20% chance that it's living somewhere over there. And there's even other chances that it's in all these different places. So we know where it's probably going to be, but we can't know for sure. Another classical example of quantum mechanics is a cat box. And you don't know if the cat's alive, or maybe if it's dead. I hope that cat's alive. Anywho, Bohr model versus the quantum model. Let's talk about that more. The main way they really differ is in the description of the electrons. In both of these, we talk about the nucleus the same way, because the nucleus is big enough that it's not really super great to model with quantum stuff. The Bohr model relies on these classical mechanics with these tight fixed orbitals for our electrons. As I just said, they're in their nice tight orbitals. They travel in a nice orderly fashion, set distances from the nucleus. The quantum model, however, says that the electron's position cannot be 100% known. And so we use math to calculate places the electron might be and the probability that the electron will be in those specific places. And we can use these calculations to create 3D images showing where the electron is most likely to be found. Like the Bohr model, the quantum model still relies on shells. And our shells are numbered just like they are in the Bohr model, and they hold the same number of electrons just like in the Bohr model. The difference here is that our shells are going to be chopped up and divided into subshells. It's a pretty good name. It's not super awful. So we have different types of subshells, which we'll talk more about. The S, the P, the D, and the F subshells. And each can hold their own specific amount of electrons. This is where the quantum model gets a little bit complicated. Also, as I mentioned, we can do these 3D images for where the electrons are likely to be found. Well, all of our different, hey, thing, get out of my way. All of our different S, P, D, and F subshells have different shapes. And that's pretty nifty. So here's just a look of how our quantum model and our Bohr model differ. Over here, we see our quantum model with just like all these random little dots. And the dots get fewer and fewer as we get further out. And those dots represent positions that electrons are likely to be. So we can see it's most likely our electrons are somewhere in here, as opposed to our Bohr model where it says like, yo, the electron is going to be traveling along this ring. In our quantum model, we're just like, it's going to be at one of these spots. It's going to be somewhere in there. It could, who knows? We don't know. We know where it might be. We know where it's probably going to be. It's probably not going to be way out here. It's probably going to be somewhere in there. So the quantum model, A lot of uncertainty in there. Here's a kid who's surfing with his pet pig, and that pig's baller, and so is that cat who's friends with that pig, and they surf together. I love stuff. Anyway, let's talk about not just subshells, but let's bring orbitals into the mix in this slide. So we'll start off with talking more about subshells. We said there are those 4 types, the S, P, D, and F, and we said they could hold different amounts. Well, the S type can hold 2 electrons. The P can hold 6 electrons. The D can hold 10 electrons. And the F, which we're not going to show a lot of love to, but is very cool, it can hold 14 electrons. I mean, it can hold 14 electrons. It's probably really cool, right? It is. It's very cool. And so each shell is made up of 1 or more subshells. So our first shell, which can hold 2 electrons, how many subshells do you think that is made of? And what type of subshell? Think about that for a second. Well, hopefully we're like, yeah, if there's 2 electrons in our first shell, it's got to have just a S subshell in it. That is correct. The first shell is just 1 S subshell, and it can hold 2 electrons, and that's all. Well, our second shell, we know can hold our second shell can hold 8 electrons. What subshells do you think make up the second shell? Pause the video and think about that for a second. Sweet. Well, hopefully you said, all right, if there's 8 electrons in that second shell, it must be made of an S and a P, because 2 plus 6 gives me 8. And you were awesome sauce and thought that. That is true. The second shell is made of an S and a P subshell. 2 plus 6 electrons gives us 8 total electrons for that shell. Well, our third shell, why don't we pause the video and think, what subshells would that be made of? Sweet. I hope you came up with an S, a P, and a D, because our third shell holds 18 electrons, and if we do 2 plus 6 plus 10, oh my gosh, that gives us 18 electrons. If we went on to our fourth shell, you probably guessed it, we'd get an F in the mix. Cool. Well, these subshells are in turn made up of orbitals. If it wasn't complicated enough that the shells are made of subshells, the subshells are made of orbitals. They're not as spicy though. Orbitals are a little bit more straightforward. Each orbital holds 2 electrons. Done. 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 Nice. So the S subshell, which is made of orbitals, is just 1 orbital, because our S is 2 electrons, and if an orbital is 2 electrons, there's 1 S orbital. Each S subshell is made of just 1 S orbital. If we look at our P subshells, they hold 6 electrons, therefore there must be 3 orbitals that hold 2 electrons each. 3 times 2 is 6. So our P subshells are made of 3 distinct looking P orbitals. So each P subshell is going to have 3 distinctive P orbitals that make it up. If we went on to our D subshells, well, there's 10 electrons in a D subshell, which means there will be 5 orbitals, and they're going to be 5 distinctive looking orbitals. Let's take a gander at one of those. So here's just, again, our Bohr model, simple shells, nice and easy peasy. Label those shells 1, 2, 3. Our first shell we know is made of 1 subshell, an S subshell, which is made of 1 orbital, and it looks just like that little smear. It's just a little smear of electrons. If we look at our second energy level, or our second shell, that's made of an S and a P. Our S orbital in the second shell looks a little bit different. And our P orbitals look kind of weird like this. Let's look at those P orbitals. Here's what our 3 P orbitals look like. These are what the 2 P orbitals look like. The 2 Ps. We'll talk more about that later. And they all combine together to make this whole big guy. And if you want to talk about something that's complicated to look at, here are our 5 D orbitals, what these dudes roughly look like. And those dudes, I like this one the most. And those dudes all combine together to make this awful looking mess. So we're not going to get too crazy about what these orbitals look like and their shapes, but I did want to show you that because it is pretty interesting, at least in my opinion. What is really important to know, and I think take away, is that our subshells are related to the periodic table. Each subshell is related to a particular part of the periodic table. So we said we have S, P, D, and F subshells. Well, S is associated with this area, P is associated with this area of the main group, D is associated with our transition metals, and F is associated with our rare earth elements. And so this is going to matter when we study when we study electron configurations. So elements that are found in the S block have their highest energy electrons in S subshells. Elements that are found in the P block have their highest energy electrons in those P subshells. And so that's important because remember, our highest energy electrons are going to be those valence electrons, and those valence electrons are the ones that do all the interesting chemistry. Neat. All this stuff ties in together. Very nice. Anywho, that is the end of this video. I hope you understand a little bit about how quantum mechanics and classical mechanics differ, how that makes the Bohr model and the quantum model differ. I hope you understand how the quantum model is composed of shells, which are composed of subshells, which are then composed of orbitals. And I hope you enjoy that pig and cat surfing duo. Anyway, ta-ta, have a great rest of your life.